Well, thank you very much. It's an absolute pleasure to come and talk to you today. And it's been just a real scientific adventure that I'd like to tell you about. A lot of fun projects I've been involved in. It's been an adventure in the grandest sense of great stories, in that there have been twists in the tale, there have been elements of conflict and resolution, consensus forming, and then, of course, further conflict. And I hope to tell you this grand tale today. It's certainly been a fun process for me. It really starts off with this key paper that came out in 2006 by Worm et al., where they looked at the proportion of fisheries with catches below 10% of the maximum. You can see that in the top black line going along there. And this paper really engendered a lot of controversy because they extrapolated forward this line into the future to obtain, as Time magazine put it, oceans of nothing, or to paraphrase their press release, all fisheries will be collapsed by 2048. Now, you can imagine that not everybody was in agreement with this. Some people that are very reasonable and diplomatic, like Ray Hilborn, said some very reasonable and diplomatic things like, "That's just mind-boggling stupid," to the press, no less. And so you can imagine my complete shock when Ray came to me a few months later and said, "You know, I sat down with with Boris Worm the other day, and, you know, he's actually a perfectly reasonable kind of guy. I could work with him." I looked at him, I said, "Are you okay?" And he said, "Look, we're going to form a working group to try and reach some kind of consensus as to what the status of global fisheries is." And they did, and I helped out with some of the work there. The basic idea of this working group, which was under the auspices of NCs, was the idea of gathering together data on catches and surveys, stock assessments, and ecosystem models to try and form a picture of what's happening in the oceans today. And they were very successful. The sort of overarching theme that came out of this was, and this is exemplified by this particular multi-species ecosystem model in one area, the idea being that as the exploitation rate goes up, you get things that happen to marine ecosystems. So in particular, of course, the number of collapsed stocks goes up, the mean length of the remaining fisheries goes down, the total biomass goes down, and of course catches, in the well-known relationship between harvest rate and catches go up, peak at some maximum, and then come down again. Now, in the old way of doing things, or perhaps I should say the traditional way of doing things, the aim of fisheries management would be to hit the point that maximizes catches. And who cares about the rest of the parts of the ecosystem? Who cares about collapsed species or average size in the system or the total biomass that's there? But working in this group that combined conservationists and fisheries people, it really was quite interesting, because whereas the fisheries people would say, well, you're only declining by 50% to get MSY or 60% to get MSY, the ecologists would say, oh my goodness, that's terrible, you've totally trashed the ecosystem. And so this traditional target that was there, you can imagine if you get things wrong, you'd end up somewhere out to the right at high exploitation rates, but that's fine if you're a scientist, because you can always get a paper in Science or Nature out there. But where it really should be aiming is down here at the sort of new target. Give up some of your catches, and you reduce greatly the amount of biomass that you take out, you reduce greatly the number of collapsed stocks, and the change to the average size of species in the ecosystem. Some of the other results that came out were quite interesting, not quite what we expected. So if you look at assessment biomass, that's the top left panel, or you look at survey biomass, that's the bottom left panel. In recent decades, there really hasn't been a big change in the total biomass of what's out there, of the areas we had data for. Similarly, catches go up, they reach a plateau, perhaps they're declining slightly now. So those are sort of the almost good news parts of the story. The bad news parts of the story are that, yes, indeed, average length of species out there is going down. That's the blue line on the bottom right. And the number of collapsed stocks is going up. That's the red line on the bottom right. So there's a good news, bad news dichotomy. The other way of looking at it is, it's like two fish stuck in a glass, and the glass could be either half full or half empty, depending how you look at it, right? In the context of the working group, it was pretty obvious that the fish with the head sticking out of the water is Boris Worm, and he's saying, "Oh, whoa, half empty, definitely half empty." Ah! And the fish with the head in the water is obviously Ray Hilborn, and he's saying, "Come on, just listen to you, always the pessimist." One of the big outcomes that came out of this working group was the development of a database of stock assessments called the RAM Legacy Database. It was spearheaded by some students of Ram Myers, hence the name, who passed away in 2007. And what they did was collate all of these assessments to give a picture of where biomass is relative to that which would produce maximum sustained yield, BMSY, and harvest rate relative to that which would produce MSY, so UMSY. And with the idea being that you should be able to see some kind of pattern where you might have lightly exploited stocks down in the bottom right, high biomass, low harvest rates. As you start fishing them, they'd end up in the top right, where you're getting to fisheries reduction. You'd end up in overfishing if you didn't hold fishing there. And if you finally ended up with some kind of management, you might end up in the recovery sector down in the bottom left. And what do we actually see? Well, we expected to see most stocks in the top left. That was the consensus before we got the data together. What we actually saw was much more interesting. That yes, biomass was low for about 2/3 of stocks, 63%, but actually most of the stocks had exploitation rates that were lower than UMSY. So that was a surprise to us. Just something to bear in mind when you look at these plots is that if you're harvesting above UMSY, it doesn't mean that your biomass is declining. It depends where you are. So this plot demonstrates that. The diagonal line is theoretical predictions from the Schaefer model, and then each square represents if your particular stock was in that square in 1 year, would you expect the biomass to go up or down in the next year? So red squares mean that most stocks in that square had biomass declining in the next year, and green squares mean that most stocks in that square had biomass that was increasing the next year. And what you see is actually pretty close to the theoretical Schaefer model prediction, which is that you can be out there above UMSY and at low biomass levels and still have stable or even increasing stocks. And that's just to demonstrate that where you go if you're in any of those zones, you tend to shift towards that Schaefer model isocline. So just in case you missed my point here about who the good guys and the bad guys are here, in this particular working group, Ray and Boris were able to pull together all of these data and look at them and come to the same conclusions. So for sure, Ray is a good guy, and that's obvious by the staggering resemblance to Gandalf. Boris is also a good guy, as you can see by his resemblance to Frodo. Now, coming almost directly out of this working group, I thought, we've collected all of these data on surveys, assessments, we have all these ecosystem models, we have catches. why not go and examine some of the other paradigms that are underlying fisheries and marine ecology? And the one I chose to look at was this concept of fishing down marine food webs. So originally the term actually comes from Willy Christensen, but really was popularized by Daniel Pauly et al. In their 1998 paper of the same name. And if you're not familiar with the concept, I'm sure you actually all are, but basically the idea is you start fishing on the predators first, deplete them, you move down to the next level in the food web, deplete them, you move down to the next level and deplete them until, as they put it, you'll just be left with a diet of jellyfish and plankton stew. I see some heads looking like, come on, give me a break. Well, I have proof that that's what we'll end up with. There's my jellyfish burger. So where does this come from? What's the underlying evidence for fishing down marine food webs? Well, there's the food web, basically the idea that trophic level 1 is seaweeds and phytoplankton, trophic level 2 is things that eat them, right down at the bottom of the food web. Trophic level 3 and trophic level 4 and upwards are marine predators. And if you assign a trophic level to each species that we catch, and you then get the weighted average globally for catches, then you get the pattern they got in their 1998 paper. And as you can see, their main result was that in recent decades, mean trophic level in catches has gone down precipitously at about 0.1 units per decade. And so the first thing I did in my paper was, I thought, well, I'm going to do the biomass side of this. We've done the catches. He's done the catches already. So I'm going to look at surveys and assessments and do the biomass side. But let me first repeat what he did and just extend it a few more years. I plotted that up, and I got something that was very different. It wasn't continually declining. In fact, since the mid-'80s, it's been increasing. And I really couldn't explain this. I couldn't explain why it was higher. I couldn't explain why it was increasing. I had to do quite a bit of detective work to figure it out. And the answer is simple. It turns out that the new results are based on updated estimates of trophic levels. So both studies were based on fish-based, and it just turns out that fish-based got better over time. We updated the trophic levels, but if you were to go back and take the current catches, but use trophic levels from 1997 for the most important species, then you get the red line, which almost perfectly matches what was in the 1998 paper. So changes in trophic levels are very important. And the most important of these is Peruvian anchoveta. It turns out the trophic level changed from 2.2 to 2.7, and that in itself was enough to change that trend from declining to increasing. Just to delve a bit further into the species that are important for mean trophic level globally, this is what happens if you look at Peruvian anchoveta catches. The catches are down the bottom in gray. If you take Peruvian anchoveta out and you recalculate mean trophic level from catches, you get the green line. So that entirely explains why you get that initial dip and then recovery in the 1960s. The dip was the expansion of the Peruvian anchoveta fishery, and the increase was when the anchoveta fishery collapsed. Similarly, that second dip and remaining in that green line over there is explained by the big increase in Peruvian anchoveta, Peruvian anchovy, where as the anchoveta collapsed, that should be sardines, sorry. The sardines increased, they occurred out of phase, and that increase in sardines results in the drop in the black line in the 80s. And then again, when the sardines collapsed, it goes up again. So taking out the sardines results in the blue line. One other species that has a big impact is Atlantic cod, and that's because it's one of the few species that actually have a nearly continuously decline in catches over time. So you take out cod and you end up with a line that instead of gradually declining with quite a bit of variability, you end up with actually the most recent trophic level in catches being higher than it was in the 1950s. So with these issues about mean trophic level being driven by one or two species, I thought it was more informative to look at the whole picture, what I call the trophic fingerprint of fisheries. Each of these black lines represents the total catch coming from a particular trophic level bin, particular group of species in a trophic level. So if you look at the top right, that's big-eye tuna and all the associated species in that same group, and you see that those catches are continually increasing over time. If you look down bottom left, you can see American oysters and all of their associated species right at the bottom of the food web, and again, all of those catches are increasing. And in fact, across all of those trophic level bins, you see a general pattern where most of them are increasing over time, with the exception of the South American anchoveta, the South American sardines, and Atlantic cod, the three big species that I talked about. The thickness of the line there is how much catch fits into that bin. So if I was to summarize how I see the change in perception now, that I would expect catches, if they followed fishing down marine food webs, to be high for the top predators, the big fish, at the start of the time series, and then those would dwindle as they are fished out. And then you shift to the next species down in the food web, and the catches of those gradually dwindle, and you shift down to the next species down. That's what I would expect to see in catches. What I actually see is a little more complex, which is that most species have catches that are increasing continuously over time. Not all, but most. So moving on from the results based on catches to some of the other work we did, we compiled, and I say we, by we I mean Beth Fulton. I could never do this. She compiled 25 different ecopath with ecosystem models and asked what would happen if you applied different scenarios of fishing to them. What would happen to mean trophic level in catches? What would happen to mean trophic level in the ecosystem? And what would happen to the number of collapsed stocks in that ecosystem? And I showed two of these scenarios here. The first is fishing down, and as you can see, indeed, if you are fishing down, you would see a decline in mean trophic level in the catches until you fished everything down to low levels. But it's a little more complicated than you thought with the ecosystem. Initially, mean trophic level goes down, and then there's a recovery. And the reason's obvious when you think a little harder about it, which is that once you've fished everything down to low levels in the ecosystem, you've got species in the same proportions they were when you started fishing. And so mean trophic level in the depleted system is the same as it was originally. Conversely, if you model a scenario where you basically increase catches uniformly across the food web on all species at the same time, you end up with mean trophic level trends in catches and in the ecosystem that are basically flat, with very little trend over time. On the other hand, though, even though there's no trend in this metric of mean trophic level, you still get more and more species collapsing over time in that scenario where we fished to the point of overfishing. So to summarize, it's a little complicated. The catch mean trophic level does not imply ecosystem mean trophic level decline. So decline in one doesn't imply a decline in the other. And even if mean trophic level is stable, it doesn't mean that the ecosystem is fine. So as an indicator of ecosystem health, mean trophic level is problematic, to say the least. So this brings me back to what I originally planned to do before this circuitous look at catches, which is to look at mean trophic level in surveys, in stock assessments, and compare those to the catch time series. And what you see is quite a bit of variability up and down, but no clear pattern of declines in any of these three series, especially in recent decade or two. Furthermore, if you do a correlation between all these series, it turns out that the catch time series is negatively correlated to the other two time series, it's a little unfair because they're not the same set of stocks. We don't have data for all the stocks that we have catches for in stock assessments or in surveys. So let's do a fair comparison, which is to take the same 223 stocks from the RAN legacy database and calculate mean trophic level for the biomass, the blue line, and mean trophic level for the catches, the red line. And what you see is, once again, the trends in these two are opposite. There's actually a negative correlation of negative 0.4, which, if you're a fisheries researcher, is a pretty phenomenal correlation to get in terms of significance. So you might ask, well, that's all very well, but what does Daniel Pauly have to say about that? Is he pleased? Well, his comments were, this paper is a hatchet job. And it's a bad hatchet job. That really offended me, a bad hatchet job. I thought it was a good hatchet job. Says Pauly, who's firing off a letter to the editor of Nature taking issue with the study. Now, that letter to the editor never made it to publication, but eventually out did come a form of rebuttal, which was part of another paper in Marine Policy, where they took this figure in my paper, where there's the original gray line with Pauly et al. 1998, there's the dark black line with the new results, and then I did some sensitivity tests where I said, well, what happens if you take out the anchoveta and the sardines? What happens if you only look at species above trophic level 3.0? What happens if you only look at species above 3.25? And if you only look at species above 3.5? So you can imagine which line was picked for the rebuttal. Yes, that's right, that one. And they say in their very short bit, they say, here's the plot from Branch et al. 2010, the only one that's worth looking at, and it shows that fishing down also occurs as an unexplained phenomenon in Figure 2 of Branch et al. 2010, a paper supposed to show that fishing down does not exist. What they didn't know was that in the year that passed since the publication of the paper, someone had alerted me to the fact that the trophic level value for Atlantic cod had changed in FishBase. So FishBase 2010, the value I used, it was 4.42. It was right up there with the top tunas and sharks in the world. 2011, it changed to 3.73, and that line that they showed as proving fishing down occurs, now I guess proves that fishing up occurs. Really, these lines don't mean that fishing up or fishing down occurs. You have to look at whether the top predators have declined or not relative to the other species in the system. And mean trophic level is a misleading index of that. Just to reiterate that, I do believe that fishing down does occur in some places. I just don't think that it's a global phenomenon that occurs everywhere. And the reason I believe it is because when I was a young boy, and every holiday we used to go to some secluded beach, my dad was a marine biologist, of course, and I would go out fishing there, and back then, there were some big, big fish that you used to catch. Jokes aside, what does explain patterns of fishery development? I mean, the sort of underlying theory is that fishing down occurs because we know that top predators are more valuable than species down at the bottom of food chains. We know we get higher prices for them. I mean, there's cod versus shrimp, right? Well, it turns out that if you look at the relationship between trophic level and price, which is plotted here, and this is some work by Suresh Sethi, there is no relationship. And the reason is kind of obvious once you start thinking about it. Well, canned tuna, that's high in the food webs. Is that a highly priced thing in the supermarket? What about abalone? That's a trophic level 2.0, right at the bottom. Is that a highly priced thing? Is it a lowly priced thing? That's worth a lot. And so there's much more complexity in this relationship than you would think. So what does explain patterns in fishery development? Well, the answer is that if you take this metric of development year, the year of first development being the year in which catches first reach 25% of the maximum, and you then try and ask which factors explain that, it turns out that trophic level and size are not correlated with the year of development. So we didn't actually start exploiting big predators first. What we did start exploiting first was stocks that would yield big catches. So things that are abundant. We started exploiting those first. Yes, we did start exploiting things with high prices first. And we did start exploiting things that are found in shallow waters first. And these all make sense because these are all economic factors. You'd want to catch things that are abundant, highly priced, and easy to get to, so the cost is low. So if you multiply catch by price, you get revenue, and that's the strongest correlation of all. So that's what explains patterns of historical fishery development. That has a corollary, though, which is there still room for us to find new fisheries, exploit them more, and get more catch and more value from the oceans or not? Well, here's the plot that shows on the left the number of new fisheries developed in each year from the same analysis. On the right is the cumulative total. As you can see, the cumulative total gradually goes up more or less in a linear fashion. So we are finding new fisheries every year. That's the good news. The bad news is the fisheries we're developing for the first time are low in volume. So this is the catch you'd expect to get from the fisheries developing in a particular year. Similarly, the fisheries that we're developing since the 80s and definitely since 1990 have yielded virtually no income to us in terms of global revenues coming from fisheries. They've only added about 3% to the total revenue in the world's fisheries since 1990. So that's the bad news. We've reached the limits of what we can fish. Now I'm going to circle back around after this side route through fishing down marine food webs, or whatever you want to call it, trophic fingerprint of marine fisheries, and circle back to the Worm et al. 2006 prediction that all fisheries would be gone by 2048. Since it was published, there have been no fewer than 11 rebuttals saying that that prediction is wrong, and it's proven so controversial that even the authors don't cite their own paper as predicting fisheries collapse by 2048. So out of 55 occasions where any of the original authors were a co-author on any paper that cited Worm et al. 2006, only once was it cited as predicting fisheries collapse by 2048. So they've backed away. But let's go back and examine where this prediction came from and why it might be false. The underlying basis for considering something collapsed or not collapsed comes from what is called catch status plots. So here's one example. As fisheries develop and the catches increase, when they hit the point above 10% of the maximum catch, you'd call them developing. When they go above 50% of maximum catch, you'd call them fully exploited. And once you hit the peak and start coming down again, then you might hit a region where you classify them as overexploited, between 10 and 50% of maximum catch, or even collapsed, less than 10% of maximum catch. That seems perfectly reasonable. Until you start thinking about why it might be biased. First of all, it's impossible to be underdeveloped or developing in the most recent year, because the only way to be in that category is to be before the year of maximum catch. And you can't be before the year of maximum catch in the most recent year. It's impossible. You're either at the maximum or before the maximum. Or after the maximum, I mean. Similarly, you can't be overexploited or collapsed in the first year of the time series, because you can't be less than 10% of the maximum and after the year of the maximum in the first year. And so built into this catch status plot is the idea that you'll always start off with nothing overexploited in the first year and nothing developing in the last year. And you can show this by, a couple more slides to go. So if you apply this to global catches, this method, this is what you get. You get 40% collapsed, more than 70% overexploited or collapsed, none developing, and a very small amount fully exploited. And if you're like me and you see something like this, make your hair stand on end, right? But actually, when you compare that to the FAO status reports, you see that there's an incongruity. So how can it be that the FAO thinks that 13% of fisheries are developing and 30% overexploited in the most recent year, but this method says that 70% are overexploited and none are developing? And the answer is, well, let's do some simulations. This is something that I'm very comfortable with doing. But luckily, John Pope and Neil Starn and Jake Rice and their little group that was mentioned yesterday in John Pope's award ceremony did this for me. They basically just took a whole series of random numbers. Let's draw 50 random numbers and call that a catch time series. Do that for a whole bunch of catch time series and apply the method. And what you see is you get almost the same pattern when you apply the method to those time series as you get with the real data from FAO. It's amazing. That's maybe a little unrealistic to just take random numbers, but you get the same result if you simulate fisheries developing with different levels of effort. So this is a paper by Tom Carruthers and a group of other co-authors at the University of British Columbia, which must have been an interesting set of group dynamics, since they were basically proving one of their colleagues wrong. But they took simulated fisheries and they said, well, okay, we can simulate them, we know what the true biomass is. How often does the catch method allocate the correct category to the stocks we know the truth for? And the answer is, well, of course, if it's developing, it's impossible to get it right because you can't be developing in the most recent year. Fully exploited, you get about 17% right. Overexploited, 57, collapsed, 33, recovering, 46, and the overall total is 31%. If you think about it, random allocation would get you 20%. So it really doesn't get you much more than random allocation. What about real data? Well, let's take our RAM legacy database and say, okay, we know what biomass is, so we can get real status from biomass. That's the plot on the right. And we have catches for the same stocks, so we can apply the catch method to those catches and compare the two. And what you get is this comparison. And once again, overexploited, collapsed stocks are far greater with the catch method than the true status from biomass, and developing fisheries are virtually zero, whereas quite a few would be classed as developing using biomass methods. So, well, there's a response to this. As I said, there'd be conflict in this talk, more conflict. So they went back and said, okay, maybe our catch method wasn't so great. Let's change it and see if we can do better, just as science works. And published 2 papers, 2 different methods. There's a Froese et al. Paper and a Kleisner et al. Paper. And their conclusions, their self-reported conclusions, were that with these new methods, trends in catch data are totally consistent with trends in biomass data, that now the method provides a robust overview of fisheries, and although there was some criticism, we've been vindicated now. Well, not really. If you take the new Kleisner method and you do the same thing I did with RAM legacy database, all you find is that now there are just a small number of developing fisheries in the most recent year, and you've reclassified some of the fisheries that were overexploited to be recovering. But the same patterns are there. It's really just a cosmetic tweak. Nothing has really changed. If you look at the other method and you ask, is there any retrospective bias in this method? So what I mean by this is, if we do the analysis in 2009, that's the black line in each panel, and we ask what status is for developing, fully exploited, overexploited, collapsed in each of the panels. Now what happens if we just took the data from up to 1999 and repeated the analysis? That's the dark blue line. If you took the data up to 1989, it's the light blue line. And if we just took the data from 1950 to 1959, that'd be the red line. What you hope to see in terms of a retrospective bias analysis is that all these lines are perfectly on top of each other. In other words, it doesn't matter when you do the assessment, your estimated status does not change over time. But what you actually see is very substantial patterns of bias over time. So when you did the analysis in 1959, you thought there were almost no developing fisheries in 1959. And almost everything was either fully exploited, overexploited, or collapsed. But as it turns out, when you did the analysis in 2009, it turned out that most fisheries in 1959 were actually developing, not fully exploited or collapsed or overexploited. So there is still substantial retrospective bias in the new method. Now, as this whole debate was going on, Boris Worm contacted me and said, you know, maybe it's time for us to reach consensus again. It seems like everyone's getting a bit confused about what the status of fisheries is. Why don't we try and write some kind of consensus paper together? And so we did. It just came out online in Trends in Ecology and Evolution. And this plot shows what happens if you take the FAO status reports and you convert them into biomass relative to unfished biomass, B0. And you do the same with our RAM legacy stock assessments. And the answer is, and this is pretty well known for the RAM legacy ones, is biomass is now somewhat below BMSY. I've put the range as a pretty wide range here, but stabilizing in recent years. Whereas if you look at FAO status reports, they're continually declining, yet higher than you would get from the RAM legacy assessments. Now bear in mind that we only have assessments basically from Europe, North America, Australia, and New Zealand. Those are the chief sources. So these are all places with a long history of fishing, but a very different style of management and intensity of management than in the rest of the world. And so what this suggests is that possibly the rest of the world that we don't have good assessments for may be somewhat better off now, but with a future trajectory that's getting worse. Whereas the ones where we do have good data are somewhat worse off now, but stabilizing or maybe even getting a little better. On the other hand, we know that there are limits to catches. So we know that we won't be able to catch much more than we're catching right now. We've reached a plateau, catches are declining already, and yet global fishing effort, the red line, is going up continuously. So we really need to think about cutting back on effort, not fishing as much, and not wasting our time and effort. So let me come back to that point about where do we have data and where do we not have data, and make a suggestion that I think is a little bold. The RAM legacy stock assessment database is dominated by, as I said, Europe, North America, Australia, New Zealand, and very little from Africa, Asia, or South America. And the situation is pretty much the same when you look at all of the trawl surveys that I compiled for the trophic fingerprint paper. Lots of trawl surveys from Europe and North America, and very few from Asia, Africa, and South America. So if we really want to get a hold of what's happening at a global level, we need data that tells us what's happening. And so what I propose is that what we really need is a global fleet of scientific survey vessels. The idea would be set up a fleet that could go and survey the world roughly every 5 years. All of the large marine ecosystems where we don't have data now, go and survey those every 5 years. Now, I got some data. Turns out the research vessel Fridtjof Nansen costs about $7 million US a year, and that can survey about 3 large marine ecosystems every year. And they're the only people that are doing this right now. There's one vessel. That's not enough. If you were to scale this up and ask how much would it cost to do the whole world, all the unsurveyed large marine ecosystems, it would cost about $23 million a year. Now, FAO and Norway are in charge of the Fridtjof Nansen surveys. Maybe they're the people that could jumpstart this. I lay this out to the hosts of the conference. I'm not going to do it. I'm a theorist. But what really needs to happen is currently the Fridtjof Nansen gives the data to the countries that do the survey in, and it can be quite difficult to get access to those data if you're an outsider and you want to figure out what's going on where they've done surveys. So the idea of this survey vessel would be give it to the home countries for the first few years and then make it open access to everybody. I can see all of you are thinking, $23 million, that's a lot of money. Who has that kind of money? Well, you know what? Pew has $250 million a year they spend. The Global Environmental Facility, $500 million a year. They spent $18 million last year to develop marine protected areas in Brazil. Well, the US paid for a telescope last year, $9 billion. And we spend 1,000 times that amount every year in subsidizing our fishing fleets. Surely we deserve a little more to actually discover what's going on with their status and trends. So that's all I have to say. I have some acknowledgements, and I open the floor to any kind of scary questions you have.